Okay, yeah, R.6. Okay, R.6. Okay. R.6 is exponential and logarithmic functions. Okay, so let's focus on the exponential. Okay, let's look at the definition of an exponential. Okay, so the definition of an exponential is an exponential function okay, f is given by f of x is equal to a b to the x, okay, where x is any real number, okay, where x is any real number okay. I'm just gonna take attendance based on who's logged in to my session, if that makes sense. It generates a report for me at the end. Okay. Does that make sense? So it generates an attendance report. Zoom does. So you're good. Okay, exponential function f is given by f of x equals a b to the x, where x is any real number. Okay. B is the base. B is the base. I should say b greater than 0 is the base. I don't want b to be a negative number because then things get really messy. B greater than, I don't want it to be 0 either, otherwise it gets very roll. No, I take roll based on a report that is generated by Zoom. Okay, there you go, by Zoom. I had to take attendance the first week to see who I needed to kick out. Okay, but everybody's in now. We're good? We're good. Okay, b greater than 0. Okay, the base is the base. Okay, and a, oh, and the y-intercept is 0a. It's a 0a, because if x is 0, then anything to the 0 power is 1, and then a times 1 is a. Okay, so let's look at this one here. Number 1, graph the function y equals, which is f of x, equals 2 to the x. So y and f of x are the same. Okay, okay, so f of x equals 2 to the x. That's what the y value is. Maybe I'll get rid of that. Okay, so if I say x and f of x, right, think of that as my y value. Okay, let's plug in some numbers here. If x is 1, okay, then 2 to the first power is 2. If x is 2, 2 to the second power is 4. So what's the point? Okay, the point that I would have to have is x comma f of x. Supposed to be 1 comma 2. This would be 2 comma 4. Okay, 3, we're going to have 2 to the third, that's 8. So 3 comma 8. Okay, 0, oh, that's 1. 2 to the 0 is 1. What about negative 1? Negative 1. What's 2 to the negative first power?
1/2.
Yeah, very good. It's equal to 1 over 2 to the first, which is 1/2. So this would be at negative 1, 1/2. Okay, very good. Okay, so what about negative 2? Okay, 2 to the negative 2 is 1 over 2 squared, which is 1/4. So if I get these negatives, I'm going to get the positives just over 1. Or is under 1, I should say. 1 over the positive value, right, if it's a negative value. Okay, so this is 1/4. And then what about negative 3? Yeah, that would be 1/8. So this is negative 3 and 1/8. Okay, so what happens if we want to graph this guy? Okay, so we have this graph here. We're going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so at 1, I'm at 2. At 1, I'm at 2. Okay, so there's a point there. At 2, I'm at 4. Okay, so there's a point there. At 3, I'm at 8. Okay, so there's a point there. Okay, at 0, I'm at 1. A point there. At negative 1, I'm at 1/2. So negative 1 and 1/2. Then I'm at 1/4, and then I'm at 1/8. And I'm just going to keep getting closer and closer to this line. And it goes up, and this is an exponential curve. Okay, it starts going up really fast. Okay. And this is y equals 2 to the x power. Right, that's that graph there. Okay, let's look at an application of this. Oops. Come on, move up. There we go. Okay, number 2 here. Move over. Number 2, in business, I can't spell business. Business. I am done with my business. Okay, in business, compound interest. Okay, so Bert invests $10,000 in an account. That earns 3.25% interest per year. Okay, so 3.25 interest. How would I set this up? We're going to say that it's compounding annually, right? So it doesn't tell me that it's compounding biannually or whatever, okay, or semi-annually or anything like that. So I'm going to assume, okay, find the function. Okay, so let's find the function here. So I'm going to say that this is A is equal to P times 1 plus R to the T power. Okay, so this is just compounding annually, where N is equal to 1, right? Okay, so we could let it be R over N if you really wanted to. Okay, times NT. Okay, but N is 1 here. Okay, because it's just being compounded annually. Okay, so N is 1. Let's figure out what this guy is. Let's plug all this stuff in and figure out what we got here. Okay, so A is equal to 10,000, okay, times 1 plus 0.0325 divided by 1, right? Divided by 1, but that's just going to be itself, okay, times 1 times t, right? 1 times t. Okay, so that's going to be equal to 10,000 times 1.0325 to the t power. Okay, so I'm going to label this A of t is equal to 10,000 times 1.0325 to the t power. Okay, so this is my formula, okay, per compounded annually. Okay, compounded annually. So if this thing being compounded annually, then after 10 years, okay, we'll say how much how much is a sub 10, and what does this mean? What does this mean? How much is a sub 10? Well, a sub 10 is a of 10 is equal to 10,000 times 1.0325 to the 10th power. Okay, 1.0325 to the 10th power. And so this will give me an approximate value. If I plug that into my calculator, this gives me an approximate value of 13,768.94. Okay, 768.94. Okay, you can check that on your calculator. I'm not going to check it on mine because I don't want the calculator here to crash my system. However, maybe there's a simpler calculator I can bring up that won't crash my system. Let's use this calculator. Let's use the calculator that's in Windows. Okay.
I got the same number.
You got the same number?
Yeah.
Okay, good. Okay, so 10, this doesn't even have a, let's go to scientific. Yeah, so 10,000 times 1.0325 raised to, I'm gonna lock this in, pin to taskbar, there we go. I'm gonna unpin this guy. Oh, okay, what do I do here? Oh, I need to do the times. I didn't do the times. Times, okay, 1.0325 raised to the 10th power. Okay, 13, yeah, there we go. Okay, perfect. Same thing. Okay, so what does this mean? Okay, let's interpret that result. Okay, what does that mean? That means that after 10 years, there will be, okay, $13,768.94 in the account. In the account. Okay, and then let's graph. Let's graph this guy. Okay, from 0 to 10. So let's graph. See what's happening to this account from 0 to 10. Graph. We're going to go on Desmos for this. I might even just do it on the graphing calculator here. Actually, let's just graph on the calculator. On calculator. Okay, t, where t goes from 0 to 10. Okay, so we want to know, well, what's the graph of this thing look like? A of t is equal to 10,000 times 1.0325 to the t power. I want to graph that. Is this thing going to graph for me? This might even graph for me. I've never used this one. Let's see. We can graph. How do I graph with this thing? What's the function? Enter an expression. Okay, so I want y equals Function? No. So enter an expression. Oh, it just says enter an expression. Okay, so let's see if we can do that. 10,000. Okay, times 1.0325 raised to. I've never used it before, so this is just an experiment. Okay, raised to the x power. Enter. Okay, so let's go back to the graph. Let's zoom way out. Okay, and so that didn't work. Let's go back to there. What did I do wrong here? 10,000 times 1.0325 to the x power. Oh, because we're starting at 10,000. Oh yeah, that makes sense. That makes sense. So we need to start at 10,000, way high. Okay, way high, 10,000. Unfortunately, this is not going to be. Okay, let's go way high to 10,000 because that should be where it starts at 0. There we go. Okay, and then I'm going to zoom in at 10,000. Boom, boom. Okay, 10,000. This thing goes. Okay. I don't know. This thing's not going to work too well. Let's try to graph it on Desmos. It's not giving me a nice curve, although I don't know because I can't zoom in enough. I don't know. It's all good. Let's see. What do I want my x to be? So I want my x's to go from 0 to 10. Okay, and I want my y's. Okay, so let's do 0. How do I delete? Back over here. Let's delete this. Okay, 0, 0. And the x's I want to be 10. 10. Okay, y min. What do I want the y min to be? I don't know. Let's say 10,000. And then let's say, I don't know. We know that it's 13,000 at 10, right? We already know that it's 13,000. So we already know what the bookends here should be. So let's do that. Let's do 10,000 should be at 0. We should get 10,000. Oops, not 100,000, 10,000, and then we should get about 13,000. Okay, 13. Let's do 14,000. 14,000. Okay. And hit enter. Okay, so let's go back to the graph. Ooh, that's a nice graph. Okay, that's good. That's what I wanted. Okay, so I can zoom in just a little bit here. Boom, look at that. Okay, right at 14,000. Boom, and 10. Nice. There's a nice graph that I'm looking for. Okay, and I can see. Oh, let me stop my sharing here. I don't know why it wasn't showing that. There we go. Okay, perfect. So when I graph this thing, okay, so I graph this function like so. Okay, I graphed it on the calculator in Windows. This is just the Windows default calculator. And I put 10,000 times 1.0325 to the x power. Okay, so I plugged that in for the function, and then I went to the graph, and then I just changed the settings here. I just, went from -2 to 11, and then not 10,000 to 15,000. Okay, you could just change the settings there, and then that gives me this nice curve. Okay, gives me that nice curve. Okay, and so that's the graph. So that's the graph there. So yeah, I'll just leave that as the graph. Okay, so what can we do with this graph? Well, we could look at it and we could see that what would a of say 6 be approximately? What would a of 6 approximately be? how much money would be in my account after 6 years. Okay, well, I could go back to the graph and I could say, hey, this thing at 6, I could kind of trace this, okay, to 6. Oops. Look at that, 12, about 12,117, I think it said. It's hard to keep my hand steady. 12,115, it's right there. Okay, I'm gonna go 12,115. Okay, so about that. Okay. Okay, let's do another one here with population. Sun just went down. Turn my light on. Okay, that's better. Now I can actually see. Okay, so let's do number 3 here. Okay, biology. Okay, population decay. Population decay. Population decay. Okay. The city has a population okay, of 15,000 people in 2012. Okay, in 2012. Assume the population decreases okay, by the same percentage. Each year. Okay, assume population decreases by the same percentage each year. Okay, yes, yeah, exactly. And that in 2017, the population was 11,250. In 2017, the population was 11,250. Okay. Okay. So okay, find a function. Okay. So A, find a function of the city's population. After 2012. Okay, yeah. So find a function of the city's population. Find a function of the city's population after 2012. Okay, so the idea here, okay, is that we have a model here. A is equal to, okay, well, we'll do population here. Okay, so the population is equal to the initial population times 1 plus a growth or decay rate. We could put plus or minus here. Plus or minus. If it's a positive R, then it's a growth rate. If it's a negative R, then it's a decay rate. Okay, raised to the T power. Okay, so P naught is the initial population. Okay, and then R is the growth or decay rate. Okay. Okay. So what I'd like to do is I'd like to calculate what this decay rate is. Okay, so the way that we're going to do this, okay, is we're going to use the information that's given to us. Okay, we're given that at time t equals 0, the population, okay, or P of t, okay, is equal to, what was it? It was equal to 15,000. Okay, and then 5 years later, it is 11,250. Okay. So this tells me that the initial population, right? The initial population is 15,000. Okay. And then it's a decay rate, right? Because it's going down. It's 1 minus R. And what's T? T is 5 years. Okay. And what's the final value here? Well, the final value is 11,250. So all I have to do is solve this equation for R, and that will give me my decay rate. Okay, and it's a decay rate because we went down in population instead of going up. Okay. So I'm going to take this guy and I'm going to divide by 25, or sorry, 15,000. It's not 25, it's 15. Okay, divide by 15,000. Okay. And then I'm going to go 11,250 over 15,000. I'm not going to round until the very end here. And then what I'm going to do is I'm going to do something a little sneaky, and that is go 1 minus R to the 5th power. How do I get rid of a 5th power? Well, I take a 5th root, or I raise this to the 1/5 power. Okay, or I can take a 5th root, either way. Okay, so that is going to cancel out with that, right? Because that's going to leave me with something to the 1st power, which anything to the 1st power is itself. So I've got 1 minus R is equal to this thing here. I'm just going to put this in air quotes. Okay, okay, that thing there. Okay, in quotes. Okay, that thing from above is 1 minus R. Now, how could I solve for R? Well, if I were to add R to both sides, I would get R plus, okay, this thing here. I would add R, right? So we would take this thing here. Let me maybe go like that. And then we're going to take that and we're going to add R to it, right? We're going to plus R to that thing. Okay. But then what I want to do is take R plus this thing here. Okay, I'll just say this thing to the 1/5 power, 11,250 over 15,000 is equal to now 1. So how could I solve for R? I could subtract off of the thing that is we're taking the 1/5 of. And we get R is equal to 1 minus, okay, subtract that from both sides, minus 11,250 over 15,000 to the 1/5 power. Okay, so I'm just going to plug this into a calculator and get what my approximate decay rate is, my rate of decay. Okay, so let's see what this comes out to be. Go back to the calculator, scientific calculator. Let's clear this. Okay, and I'm going to go 1 minus parentheses 11,250 divided by 15,000, close parentheses, okay, raised to the 1/5 power, to the 1/5. Well, 1/5 is 0.2, if you want to know. It's just 0.2, right? So I'm just going to raise this to the 0.2 power. I'm going to do the 1/5 in my head and just raise that to the 0.2 power. Okay, and it tells me this is, okay, about 0.056. So 0.056, or about 5.6%. Okay, so the decay rate, it's going down about 5.6% per year. That's the decay rate. Okay, so how could I write this as a decay model? Well, this is going to be my final population is my initial population, which is the 15,000, times 1 minus this decay rate of 0.056, okay, raised to the t power. Okay, this is going to be my model for t years. So this is 15,000, okay, times 0.944 raised to the t power, and we can make this just p of t because the only variable here is t. This is how I find the population of the city after t years. Okay, that's how we find the population of the city after t years. And notice that the base here, the base b, right? If we think of it as terms of a to the bx, right? Or in this case, t. Okay, notice that the base b is between 0 and 1. And if your base is between 0 and 1, that is exponential decay. Okay, instead of growing exponentially, okay, this is exponential growth. What you're going to get is you're going to get exponential decay. And it's just going to go down. Okay, so if the base is between 0 and 1, it's exponential decay. If your base is bigger than 1, it's exponential growth. This is for b. Growth is for b is greater than 1. And for decay, your b is between 0 and 1. It's a fractional amount for your base. Okay, so that's how that works. Okay, let's see what happens after 10 years. Okay, what is the population of the town after 10 years? Okay, part B, what is the population of the city? Is it a city or a town? It is a city. Okay, of the city after 10 years. Okay, people are moving away faster than they're moving in. Okay, guess that's what happens when you put like a nuclear reactor in your city. Everybody's like, I'm out of here, bro. I'm moving away. Okay, so welcome to Springfield. Okay, what is the population of the city after 10 years? Okay, so we have this nice P of 10, P of T function that we can use, and we just go 15,000 times 0.944 to the 10th power. And so that's approximately how many people? Approximately how many people is this? Okay. 15 grand times 0.944 raised to the 10th power, right? Boom. Okay, so that's about 8429. I'm just going to round. I'm going to say it's about 8,430 people are still left in the city. Okay, after 10 years. So it went down about half, almost half. Half the people left after 10 years. Okay. Okay, so let's talk about the inverse of the exponential function here. Okay, so if I have y equals a b to the x, the inverse of this function the inverse of this function, that would be if I would swap the y and the x. I'm going to swap the domain and range. Okay, the inverse of this function is x equals a b to the y. Oh, okay. So, so how the heck am I going to deal with this? Okay, I want the inverse of the function. Well, what we do is we create something called a logarithm, okay? And so this thing, okay, I'm going to divide by a, So this becomes x over a. Okay, so whatever number is in front there, it's just being divided by the x now. And I'm going to say x over a is equal to b to the y. And I'm going to change this now into say that this is log y equals log base b of x over a. Okay, log base b of x over a is the inverse function of the original function. So these are inverses of each other, a b to the x. These are opposite functions. One undoes the other. Okay, so if a was equal to 1, okay, maybe that makes it a little easier. If a is equal to 1, then we just get y equals b to the x and its inverse, y equals log base b, okay, of x. Okay, so these are inverse functions. Okay, they undo each other. Now, what does the exponential function look like? Well, the exponential function looks like this. What does the logarithmic function look like? I'll put it in a different color. The logarithmic function looks like this. Okay, so this is log base b of x, whereas this guy is just b to the x. Okay, so b to the x goes up, and notice that this creates a mirror image along this line y equals x. Okay, it's a mirror image. Okay. Okay. So let's understand what the inverse of this thing. So let's graph the inverse. Let's make this number 4 here. Number 4, graph the inverse of y equals 2 to the x. So what's the inverse of y equals 2 to the x? Well, that's going to be y equals log base 2 of x, right? So graph the inverse of this thing. Well, that's the log base 2 of x. Okay. So how am I going to graph that thing? Well, if I look at the original function, y equals 2 to the x, right? Then we already did this. This is when x is equal to, we'll just do the positives right now. When x is equal to 0, y was equal to 1. When x was equal to 1, y is 2. 2 is 4. 3 is 8. We could do 4 is 16. Okay, 16. 5 is 32, right? Blah, blah. Okay, and that's that guy. Now, how would I find an inverse? Well, to find the inverse, I swap the domain and range. Right? I swap the domain with the range. Oh, okay. So what was y will now become x, and what was x will now become y. So the inverse swaps the x's and the y's. Oh, okay. So y equals log base 2 of x. Okay, that means that the x's have to be the y's, and the y's have to be the x's. Oh, okay. So the x's are now the y values, 1, 2, 4, 8, 16, 32, and the y's are now 0, 0, 1, 2, 3, 4, and 5. So I just swap them. Okay. So what this is saying, if we look at one of these specifically, if we look at this log function, it says that y equaling log base 2 of x. Let's plug in some values here. When x is 1, well, let's not do when x is 1. Let's do when x is 2. Okay, so we could do when x is 1. Okay, let's plug in 1 here. So what is y equal to when x log base 2 of 0, 2 of 0? Well, what this is asking me, the question that this is asking me, when I look at it in logarithmic form, this is asking me, let me get rid of this thing, go away. Okay, what this is asking me is this is asking me 2 to the what power, 2 to the what power is 0? That's the question that I'm being asked. 2 to the what power? Oh, sorry, this is 1. This should be a 1. My bad. Okay, because x is going to be 1 there. I'm going to plug that in. It says 2 to the what power is 1? 2 to the what power is 1? Well, that's 0. Right? 2 to the 0 power. I'm looking for the exponent. A logarithm is an exponent. That's what I'm looking for. I'm looking for the exponent. 2 to the what power is 1? Okay. And that's 0. Okay. 2 to the what power is 8? 2 to the what power is 8? That's what's being asked when I go y equals log base 2 of 8. 2 to the what power is 8?
3.
3. Gabriel, thank you, Paulina. Okay, thank you, Giselle. Okay, yeah, 3, right? 2 to the what power? You can even put a little question mark there to remind yourself. 2 to the what power is 8? That's how we look at a logarithm. 2 to the what power is 8? Oh, okay. Yeah, it's 3, right? So does that make sense that the 8 would correspond to a 3? 2 to the what power is 8? Yeah, this is 3, right? 2 to the what power is 8? Okay, that's kind of what we're thinking of. If I were to plot these points, okay, when x is 1, when x is 2, when x is 4, when x is 8, okay, I'm not going to go all the way up to 16. Maybe I will. Okay, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, as far as I'm going to go here. But what's the y value when x is 1, y is 0? Okay, so that's there, right there. Okay, when x is 2, y is 1, so right there. Okay, when x is 4, y is 2, so right here. Okay, when x is 8, so this was the first 4, this is the second 4. Okay, when y is 8, I'm up another 1. Okay, so it's going like that. Okay, when y is 16, I'm up another 1. Okay, so we're getting some sort of curve that looks like this. Okay, what happens between 0 and 1 though? That's really what I'm concerned about here. Is, well, what happens, you know, when things are less than 1? Well, okay, let's see. Well, when things are less than 1, what is the log base 2 of 1/2? Log base 2 of 1/2. What is log base 2 of 1/2? Any ideas? 2 to the what power is 1/2?
-1.
Very good. Thank you, Mario. Okay, was that Gabriel or Mario?
That was Mario.
Okay, that was Mario. Okay, good. Okay, so yes, it's -1, right? -1. So that would create a point of 1/2, -1, right? So at 1/2, I would be at -1. Okay, so let's do a 1/2 here, and that's going to give me a. So this, I'll say this is 1/2. Okay, and then I'm down here at -1. Okay, what about log base 2 of 1/4? Isn't that going to be 1/4 -2? Right? So 1/4 negative. So if we did -2, that's going to get, right? Am I ever going to be able to get to 0 in the x values? Am I ever going to be able to get to 0? No, I'm just going to be, no matter what the y values are, okay, as the y values go down, -3, this thing's going to be 1/8. And then -4, this thing's going to be 1/16. And so on and so forth, right? And so I'm just getting a curve that's increasingly approaching 0, but it will never get to 0. Okay, which brings us to a property of logs, okay? If I have y equals log base b of x, then, okay, then x, okay, has to be greater than 0. Okay, I cannot plug in a value. Okay, I cannot plug in a value that is negative or 0. It's not in the domain, right? So what's the domain here? The domain, okay, goes from 0 to positive infinity for any logarithm. Okay. Okay, so let's look at some properties of logs real quick. Okay, does that make sense? That you can't, so if I plug in a negative number here for x, it doesn't make sense. You can't take the log of a negative number. It does not make sense. Okay, just doesn't make sense. Okay, you also can't take the log of 0. That also doesn't make sense. Okay, what, right? Because what is this asking? If I plug in a 0, what is this really asking? We have log base b of 0. This is asking b to the what power is 0? Well, can I ever get 0 by raising b to a power? No. B to what power is 0? Nothing. It's not equal. Okay, b to the what power is 0? Nothing. That's asking. I also can't get any negative numbers. I can get fractions though. All I have to do is raise it to a negative number, right? So I can get fractions. Okay, but I can't let x be 0 or negative. I can't let my output, okay, be a negative number or 0. Why? Because if we look at our exponential, right? Look at our exponential, what can the range not be here? Well, same thing. The range can't be, it's going to approach 0, but it's never going to get there. So the range is always positive. That means in the inverse, the domain is always positive. Okay? So again, if we look at our two graphs, this is my exponential, and this is my logarithm. Okay, we'll do a b to the x here, right? So if this is going to approach 0, then this approaches 0. Okay, if the y values approach 0, then the x values approach 0, right? When I swap domain and range. Okay, anyway, enough of that. Let's get into the nuts and bolts of this. Okay, so let's do properties of logarithms. Properties of logarithms. Okay, properties of logarithms. Okay, property number 1. Okay, property number 1 is that if I take the log base a of m times n, okay, I take the log of a product, then this becomes a sum. This is log base a of m plus log base a of n. Okay, number 2, so a product becomes a sum. Product to sum. Product to sum. Okay, multiplication implies addition. Multiplication implies addition. Okay, what about log of a of division? What do you think division is going to imply?
Subtraction.
Yeah, exactly. Okay, So exactly. So this is log AM minus log AN. So we said that division implies subtraction. Oh, okay, that's cool. Okay. So let's look at number 3 here. So we have log base A of M to the B power. Okay, M to the B power. Well, this is what? What is repeated multiplication? Repeated multiplication is exponents, right? So this is just being repeatedly multiplied, right? So isn't this just the log base A of M times M times M times M times M B times? Does that make sense? Isn't that just B M's? Okay. Okay, right? So that's just multiplying M B times. But what did we say multiplication implied?
Addition.
Yeah, it implies addition, right? So what happens when I add M B times? Right, because isn't this going to become log AM plus log AM plus log AM, and isn't that going to be added B times, right? So how do I do fast addition? Isn't fast addition what?
You just put the B in front of log to
Yeah,
say
why?
how many times it repeats.
Because isn't fast addition multiplication? If I wanted to add 2 plus 2 plus 2 plus 2 plus 2, isn't that 5 2s being added together? So wouldn't I just multiply 5 times 2? Does that make sense? So this is going to be equal to B times the log base A of M. Oh, okay. So that becomes the log base A of M to the B power is equal to, we can just basically put the B in front, right? That's kind of the way we're thinking. Okay, if you had to teach this to a 5th grader, you wouldn't go through all this. You would just say, hey, here's the rule. If you see a log to a power, put the power in front. Drop the power down. Put the power in front. This is B log base AM. Okay, so that's the rule. It's rule number 3. Okay, rule number 4. Okay, log base A to the A, or log base A of A, is equal to what? Well, it's equal to 1. Why? Because what is this asking me? This is saying A to the what power is A? Oh, A to the what power is A? 1, right? A to the first power is A. That's what it's asking. Oh, okay. So let's do number 5 here. Okay, log base A of 1 is equal to what? Log base A of 1, anything to what power is 1?
0.
0, exactly. So this is 0. Okay, number 6. Okay, log of M equals, if you don't see a base, does anybody know what the base is?
10.
10. Okay. So I'm going to ask Gabriel that since you are so brilliant, that you would just wait maybe 5 seconds, just count to 5, and then you have permission to answer. No, it's all good. It's all good. I just want to make sure that, you know, there are other people that get opportunity to answer. Okay. So, because I already know that you know all this stuff, you know, and that's not the point. The point is not to review stuff that everybody already knows. It's to make sure everybody's on the same page. Okay. So, I mean, I love the participation. I just want to make sure that everybody has equal opportunity to share. Okay, log base 10, right? So if it just has a log, just like on this calculator, if I bring up the calculator here, does this have functions, log functions? Yeah, it does. Look at this, log. So what is log? Clear. Let's do clear here. Clear. So what would, let's say that we wanted the log base 10 of 100. What do you think that's going to equal? Log base 10 of 100. 10 to the what power is 100?
10 to the 10?
10 to the second power, right? 10 to the second power is 100. Does that make sense? So if I did log of 100 on my calculator, log of 100, let's do 100 and let's take the log of it. Look at that. Isn't that 2? So if you just have log without a base, it's assumed at base 10. Okay? And the reason that it's assumed base 10 is because we have 10 fingers. Okay, and we use base 10 as our number system. Okay. Okay. Number 7 here. Number 7 is a nice formula to have. Okay, it's called the change of base formula. Log base A of M is equal to log base B of M over log base B of A. Interesting. Okay, and normally what we'll do is we'll just say on the calculator, we'll say this is log base 10 of M over log base 10 of A, or log M over log A, right? So log A base A of M is equal to the log of M over the log of A. Okay, so that's called the change of base formula. Change of base. Okay, because we're just changing the base to figure out what this is, and this allows us to use a calculator to get any answer. Kind of cool. Okay, for example, if I wanted to find out what's the log base 2 of 8, well what is that? What's the log base 2 of 8? Two to the what power is 8?
3.
There you go. Good job. Thank you, Justin. Thank you, Darlene. Okay, so this should equal 3, right? So does this work if I plug it into the calculator? Right? This should be equal to log of 8 over log of 2. Does that make sense? Log of 8 over log of 2. Oh, okay. So what is this going to work? Okay, log of 8. Okay, so let's do, I'm going to clear this out. I'm going to go 8 log divided by 2 log. Okay. Oh, did I mess up? Log of 8 over log of 2. Why is this not working? Doesn't make sense. Go back here. Did I mess up somehow? That doesn't make sense. Okay, this should be log base 10 of 8 over log base 10 of 2 should equal 3. Why is it not working on the calculator? Let me look it up on my other calculator. Not a weird one. Okay, so log base 8 divided by log base 2. That comes out with 3. So this calculator came out with 3. You can see that. Probably can't see it. Okay. Wait. Okay, so let's why is it not working on this one? This is a weird calculator. Okay, let's put parentheses. Okay, maybe that's the problem. Okay, log, oops, clear. Okay, so I want log of 8, log, clear it. Parenthesis 8 log, it's because it's got reverse notation, which is really weird. Okay, divided by, okay, parenthesis, log No, didn't want that. Okay, I think I know what's going on here. Okay, so log here, 8 log divided by 2 log. What the frick? Making logs of logs. Okay, let's try this again. Last time, and I'm giving up on this calculator. 8 log divided by 2 log equals, boom, 3. There we go. Okay, worked. Okay, it's just a weird calculator. Okay, so it equals 3. Boom. Okay. Okay, so let's look at number 8 here. 8th property of logs. Okay, log base A of a to the k. Okay, what do you think this is going to be? Well, we can put the k in front, right? Can we put the k in front? K times log base a of a. But what was log base a of a?
Is it just going to be K?
What was it?
Is it just going to be K?
I can't hear you. I'm sorry. You're all muffled.
Hold up.
It was 1.
Yeah, it should be 1. Okay, it should be 1. Log base a of a, it's asking me a to the what power is a? A to the what power is a?
1.
So this is just k times 1, which is k. Oh, okay. So log a to the ak, log a of a sub k, or a to the kth power, okay, log base a of a to the kth power is equal to k. Okay, so they undo each other. Okay, very similarly, if I take a to the log base a of k, okay, this also ends up being k. Why? Why is that? Well, it's because what's being asked here, okay, of log base a of k, log base a of k, what is that being asked? That's a to the what power is k, right? A to the what power is k. Okay, so this whole a to the k, a log base a of k, I'm going to make that my question mark. That makes sense, right? I don't know what that is. I'm just going to make it a question mark. But I do know that if I translate this, a to the what power is equal to k, right? A to the what power is k? A to the what power is k? That would be the answer to this. So I'm just going to let this guy, right? I'm just going to let this guy be the question mark. So this is a to this question mark. This question mark is that question mark. Does that make sense? But what do we know that a to the question mark is? It's k. We know that these two undo each other as well. So a to the log base a of k is equal to k. These cancel each other out. So you can essentially think of this guy and that guy canceling each other out, and this guy and that guy canceling each other out. So those are our properties of logs. Good, good, good. Okay. So let's do a problem here. Okay, let's do a business application. What are we on, number 5? I think we're on problem number 5. These are properties, not problems. Okay, let's do problem number 5 here. Okay, Bert and Ernie. Okay, no, just Bert. So this is another business application. Business application. of compound interest. Compound interest. Okay. Business application of compound interest. Okay. Bert, okay, deposits $10,000 in a savings account. Okay, at 3.25% interest. Oh, look at that. Okay, I've seen this before. Okay, nice. After how long will Bert have a balance of $20,000? How long will it take for Bert to double his money to 20,000? About how long is it going to take him to double his money to $20,000? Okay, so let's think about this for a second. So compound interest, right? So A is equal to P times 1 plus R to the T power. Okay. Okay, so we're just going to do compounding annually because they don't tell us that we're compounding weekly or biannually or semi-annually or quarterly. They don't tell us that we're compounding quarterly, so we're just going to assume that it's annual compound interest. Okay, so A is equal to, well, let's plug in what we know. Okay, I know that I'm going to invest $10,000, right? Okay, and I know I'm going to invest that at 3.25%, so 0.0325. Okay, over a certain number of years. And what I'm really looking for here is the years. What? The years of what? Well, the years that it's going to take to double this money. Right? Okay. So let's think about this for a second. Okay, so this is going to be A. Well, what is the final amount that I want? What is the final amount going to be?
20,000.
Yeah, exactly, 20,000. Okay, so 20,000. Okay, and so oops, this is T. Okay, so I'm going to try to solve for T here. Okay, so this is going to be divide by 10,000. Okay, and so yeah, this is 10,000, and then divide this by 10,000. So this becomes 2 is equal to, okay, 1.0325 to the T power. Okay. Now what I want to do is I want to change this into logarithmic form. I want to change this into logarithmic form. How can I change this into logarithmic form? So think of this now as y equals, okay, y equals a to the x power, right? Okay, so how could I change that into logarithmic form? Well, this would be x equals log base a of y. That's how I would change this into logarithmic form. Okay, so I would let this guy be the base. This is the base. Okay, this is the base, right? And then, so we're saying that t, right? T is x in this case, right? So t is equal to the log base 1.0325 of 2. Does that make sense? Okay, I rearranged to put it in logarithmic form. Okay, it went from exponential form into logarithmic form. Okay, okay, solving for what? Okay, I mean, maybe it's a little easier if we do this. 2 to the third is 8, right? So wouldn't I say that 3 is equal to log base 2 of 8? Does that make sense? So I change this, which is exponential form, into logarithmic form. Does that make sense? So maybe we'll just get rid of that and keep the numbers, right? So does that make sense that if I wanted to solve for 3, couldn't I just change that into an exponential, right? 2 to the what power is 8. Well, 1.03 to the what power is 2. Well, that's log base 1.0325 of 2. Does that make sense? Hopefully that makes sense. Okay, so just changing it from exponential to logarithmic. Okay, so changing from exponential to logarithmic. Okay, so how can I solve this? Well, I don't have, okay, I don't have a base 1.0325 on my calculator, but what I do have is I have a log button of base 10. So isn't this going to be the same thing as log of 2 over log of 1.0325, right? That change of base formula. Now we can go to the calculator. Okay. We can go to the calculator now. It lets me. And I'm going to say log of 2, clear. Okay. Log of 2 divided by 1.0325 log equals, and this comes out to be about 21.67 years. Okay, 21.67 years. Okay, years. So it's going to take about 22 years to double my money invested at 3.25%. So at 3.25%, for 21.67 years, I will double my mom. Bert, not I. Bert and Ernie. Bert will double his money. Okay, has anybody ever heard of the rule of 72? Anybody know what the rule of 72 is?
Yeah, I was gonna ask you if you thought it was valid or.
Divided by 2.
Yeah, the rule of 72, and we'll get to why this works next time. Okay, actually we won't. We'll go back to this in chapter 2, but the rule of 72, and we'll see why this works a little bit later when we talk about natural exponents and logarithms. Okay, but the rule of 72 says that if you take 72 and you divide by your interest rate, R, right, as a percentage, that will give you the time to double. It's approximate time to double. Time to double. Okay, so say that you invested at 8%. How many years is it going to take you to double your money? Well, what's 72 divided by 8?
9.
9. So this is approximately 9 years. Okay. 9 years. And again, we'll revisit this and see why this works. Okay, but this is kind of like showing it up here. Well, if we take 72 and divide by 3.25, approximately how many years is that? Okay. So 72 divided by 3.25 comes out to about 22 years. So does it work?
Yes.
Yeah, it gives you a rough estimate. Okay, rough estimate. Okay, now it's not always going to work. For you know, it's going to give you within plus or minus one or 2 years. Okay, it's a ballpark average. Okay, and then later on I'll describe why this works. Okay, but it works. Okay, the rule of 72. You just take your interest rate, divide by 72. Take 72 divided by your interest rate, and that's the time to double your money. Okay, I'm going to stop there. That's it for me. If you have any questions, let me know. But make sure that you're completing the homeworks, and yeah.
I wanted to ask if you took roll. I came a little late. So
No, the program Zoom takes roll for me.
Oh,
Okay.
all right. Thank you.
Yeah, sure, absolutely. Oh, Buster, you want to see Buster again? Okay. He's on the bed, but he's like, he's right there. He wasn't on my chair today. He's all, so he doesn't know what's going on. So all he sees is some sort of bright light. Right? Okay. Move toward the light. Move toward the light. Okay, anyway. Okay, I'll put him on my chair. Okay, there we go. Yeah. See you later. See you Tuesday.
Bye. Thank you.
Bye, you're welcome.
Professor.